Fraud constitutes a pernicious problem across numerous domains, manifesting as fake product reviews, resale of stolen goods, collusion among scientific peer reviewers, and fraudulent payments, among many other types of fraud. In many of these domains, the problem is primarily handled by automated detectors that operate over graph-structured data. Although many organizations dedicate entire teams to fraud detection, other organizations outsource the development of fraud detection mechanisms to third parties such as academic researchers, vendors of fraud detection software, or external contractors. However, effective outsourcing requires enterprises to share internal fraud data, which can be challenging due to privacy regulations like GDPR and/or the risk of leaking trade secrets through shared datasets. As a result, the lack of publicly shareable data has limited research progress on detection of fraudulent behaviors in privacy-sensitive domains. In this work, we explore a paradigm for outsourcing fraud detection in which data does not leave an organization's boundaries. Instead, third parties submit fraud detection algorithms based on existing techniques, including domain knowledge and public data, which are evaluated by the data holder on their private dataset. The data holder returns a single or multiple accuracy statistics to the developer, like false positive and negative rates or the AUC score. Naively, this system appears to prevent third parties from learning private details of the data holder's graph, since a third party only observes an accuracy statistic for a fraud detector submitted to the system. In fact, as we show in our work, there is a simple but highly effective privacy attack on this system that allows a third party to infer the presence or absence of an edge between any two vertices in the graph. Concretely, suppose that a third party wants to learn if Alice and Bob are connected in the data holder's private graph. They submit a corrupted fraud detector to the data holder. Then, we show that based on the accuracy statistic the third party observes, they can infer whether or not the edge exists between Alice and Bob or is absent in the private graph data. In our KDD paper, we precisely define the privacy attack I have described and show through simulations of a deployed facial recognition benchmarking system that this attack is practical in a real-world setting, achieving near-perfect accuracy in identifying whether individuals' data is present in a private dataset. We then evaluate the potential of differential privacy as a solution concept for preserving privacy of graph data used in a benchmarking system. Check out our paper and presentation at KDD 2025 to learn more.